Welcome everyone. Sorry for the slight delay. It's a pleasure for us to, in the IMC seminar, to have today Professor Rashmi Vinayak. Did I pronounce it correctly?
Yes.
Yes. He's a professor of computer science at Carnegie Mellon University. She obtained a PhD in Carnegie. She has many awards in her name. They're only her bio, but notable awards are the Sloan Research Fellowship and the IEEE Goldsmith Lecture in 2023. Those are the most recent ones. Oh, and you also and it's a career. Yes. Your undergrad, where was your undergrad?
In India.
Oh, in India.
Yes.
So let's welcome her with an applause.
Hi everyone. Sorry for the slight delay. I hope to make it up. We moved out our day with interesting. So before going into first of all, thank you very much for the introduction. This is my first time in Chile, and as I will show, I came to know about the university where a big chunk of the talk that I work with. And before going into so before going into the technical, just a very quick introduction. Since I see a new Carnegie Mellon. So we do research both on the theory as well as the systems. We work on theoretical problems which are based on real systems challenges in the systems, and then solve the theory problems and not just stop there, go and use those tools in building real systems. And on the theory side, the research in the group is information theory and coding theory. And on the system side, we focus on elaborating concepts and kind of resource efficiency in various levels of storage, caching, and machine learning. Okay. So in today's talk, I will see a brief introduction to what coding and what it's a very and then we will go into how coding tools are used in the real world systems. And then in the end, the European Union is one of the most recent research projects in this research. Okay. So let's start with the first one. So at the top here, I have a sentence, right? But with some letters below. What do you think this sentence is? Yeah.
Welcome to the talk.
Awesome. Welcome to the talk. That's good, right? So why did this work? Even though I didn't have all the inputs, but still you were able to read what, right? So why do you think this work?
Yes, we assume that these are the words that we have to go.
Right. So you're going in the right direction because English language has certain structure and we use only certain words and rhythm, right? So you cannot have arbitrary letters. So if we go a little bit one more level deeper, this structure is basically that it has some redundancy. So it's not all possible words that we can construct using the language. Right? So there are only some things that are possible. So there is built-in structure and redundancy, due to which it is okay. It's tolerant to this. Right? So in the same way, coding theory and codes are a clever way of adding redundancy in a smart way, in a judicious manner. So I will describe what this means. But the essence is similar. We want to have redundancy using mathematical tools so that we can impart error resilience for us. Okay, so let's go a little bit in more detail. So basically, coding theory provides us with mathematical tools that enable communicating over noisy channels. And what communication means and what noise means depends on application. Like for example, if we are looking at point-to-point communication, like for example, case of all internet communication, there the application is communication. Actually, the word communication refers to the application itself. And in other applications, like for example, data storage, like your digital drives, right? Or when you store data on Google Drive or Amazon S3, or when you upload photos to Facebook or Instagram, they are all stored on storage devices. That can also be seen as communication. It's just communication over time. Because you store data and you read, you want to see that data next day or next week, which is also kind of communication. Similarly, there are other kind of applications, for example, computation. Like when you perform a task in a distributed fashion across different machines, that can also be viewed as communication, where you want to run the computation in a way such that even if one of the machines fails, or even if one of the machines is slow, you still want to be able to run the computation. Okay, so these are all various different applications where polythetic tools are used. And in these applications, what is noise is different. Like for example, in the point-to-point communication example, like in the internet, the noise is due to the packet drops when you send data over the internet, packet drops. And in this drives bit corruption, that will be the noise. Similarly, there are more emerging storage devices like storing data on DNS. There other kind of corruptions occur, which are like deletions and insertions, meaning that some data that is stored, some of the bits will get deleted, and you won't even know which bit will delete. And some new bits can get inserted. So these are kind of different kind of noise models that come in different applications. So far, polythetic has had enormously in various applications. For example, cell phone communication from communicating cell phones to the base station was enabled by polythetic. Similarly, satellite communication and being able to store data reliably in the hard disk drives or SSDs, all of them are possible because of polythetic. Okay, so it has had a significant impact overall. But even then, even though there has been a lot of research since many decades in polythetic, it is still very relevant today and very useful. Only what is communication and what is noise has evolved and has changed. Okay, so let's take one example. So let's see what is the role of polythetic in today's distributed data systems. So today, as you all know, we have lots of large-scale data systems, right? So we could have data centers where we have thousands of machines running computations and also storing data. And there is cloud storage, and there is also what we call a central distribution networks, which help in distributing data on the edge of the internet. So all these large-scale data systems face many unavailabilities and challenging running atmosphere. So, for example, failures, stragglers are common, and loading paths, some of the machines will get fires, some of them low load, and so on. So there are many such non-ideal operating conditions which are prevalent in the systems. And in order to protect against that, so that these systems can still function well, redundancy is added. So, for example, you could duplicate it. So, suppose you have stored data, and if you know that some of the disks can fail, then you can store 2 copies of it, so that even if one disk fails, you still have it, right? So that's what I mean by that. So we want to do that. But that comes with a cost, right? So whenever you have redundant data or redundant computation, you have the cost of storing the additional data. Like for example, let's say you have to store 1 gigabyte data, which is very common nowadays in these big companies, whether it's Meta or Google or Microsoft. All of these have petabytes or exabytes sitting in petabytes into the 15. It becomes a huge amount of data. If they have to store multiple copies of this, it's important. It's not worth it. So the cost of storage has to be taken So whenever you have redundancy, there is additional hardware resources. You actually need additional disk drive as well. Typically, you have additional enablements, additional physical space that is needed, additional people to manage the users, and so on. So redundancy comes with a significant cost. So whenever we are adding redundancy into a system, we have to do it in a resource efficient, that is using as less resources. If we want to add redundancy, we add less resources possible, and this is where coding theory comes into it, because it gives us mathematical tools by which we can do that. So I think a very concrete example to show what I mean by codes and then how it gets used in industries. Let's take this example. So let's say we have 3 blocks with A, B, and C. So think of it maybe like 8 megabytes worth of sized chunks of data. Okay. So one approach of adding redundancy is just having multiple copies of this. Right? I could have ABC and then another copy of it. But as I just described, that adds too much over. So let's see what is an alternative approach. An alternative approach would be to use codes in order to add what are called as parity blocks. So these parity blocks are some mathematical functions of the data. So here, first parity block is A plus B plus C. And the second one is A plus 2B plus 2C. So for now, just assume that this arithmetic is just like normal arithmetic over the real numbers. Okay, so just for the sake of understanding, let's assume that right now. So in this code, we have, so the typically codes have parameters associated with them. So the 2 main parameters are K and N. K refers to number of dimensions, which is 3 here, and N refers to the total after adding the. So N is 5. Okay, so this will be referred to as the 5 3. And R typically denotes the number of parents here. Okay, so now in this code, so this code can recover from any R, which is any 2 pairs. Okay, so let's see why that is the case. So if these 2 pairs, it's easy to see because we have the original data. But suppose these 2 pairs. So is the data set. What? Can we, so we have C, which is failed with the, so this block has failed. So can we recover C? Yeah, multiple of you are saying yes. Can one of you say how?
By subtracting A and B.
Yes, by subtracting A and B from the first value, right? Very good. So similarly, you can actually work out and see that for any 2 failures, you can recover ABC. Okay, so the original. So let's check. So suppose B fails. This is intact. So let's say this is fine, but these 2 fail, B and C. Then we'll have A plus B plus C, and A plus 2B plus 3C. So let me do this. Yeah. So let's say B and C is failed. Can we recover B and C from A and these 2? Yes. How? Like what property of these 2 mathematical equations enable us to do that? Yeah, somebody is there. Yeah, they're linearly dependent vectors, right? Thank you. Yeah. So basically, these 2 functions have this property that they are linearly independent functions of these 3, and thus we can recover any 2 failures. Okay, so in general, in this toy example, so this is an example of an erasure code where you can tolerate any 2 failures, and the overhead is less than 2x. So if you have 2 copies of the data, you have to X the amount of resources. But here it is lesser than this, right? And in general, you can go much lower. So I'll show you an example. So here, instead of having 3 additional nodes, we have only 2 additional. Similarly, you can have much longer. So often some of the numbers that are used in practice are 10 plus 4. So you have 10 data and 4 values. There it's only 40% additional 4. So instead of 200%, where in order to meet that for relevance, you need at least 3 copies. Okay, so this is how erasure codes can help in adding redundancy in the resource. You can have less overhead, but still tolerate methodologies. So I consider this arithmetic as being done like general real number, but in reality, these constructions are done over finite fields, and the arithmetic performed here is or arithmetic non-finite. If you can see the non-finite. Okay, so this was just a toy example. And I want to give another example about what does it mean to construct a code? What does it mean to design? So here, right? So designing a code, as you all just saw, there's something about linear independence in these functions. So basically, there is this linear operations, and basically linear algebra comes in the picture, and it's all about designing matrices with certain properties. So if you think about this code, you will have the first part, which is an identity matrix corresponding to the data part. And there are some corresponding to the parity blocks. There will be certain columns here, which is be denoted as P. Okay, so this is called the systematic part, the data part, which is an identity matrix, and this is called as the parity matrix. And designing a code is about constructing parity matrices, which has. Okay, so let's keep this in mind. Later on in the talk, we will come back when designing certain. Okay, so coming back, just keep in mind, codes have 2 parameters associated with them, N and K. So you encode K messages into N code symbols. So pictorially, we will be seeing such pictures where these empty boxes are data, filled boxes are parity. So we have K message symbols and R, which is then minus the parity symbols. This entire thing together is called as a code. And codes where we have such form, where the data is in and then there is parity are called as systematic code. Almost all codes we use to practice as okay. And N is called the length, K is called the dimension, and this is an important thing. The overhead of this code is N over K. Okay, so because in order to store K, you need to store N. So N over K is. And the design of the parity matrix is such that it has to satisfy the decodable constraints. One of them, an important one, which is often used in practice, is called as maximum distance, MDS. It means that any K out of N is sufficient to recover the 3. Similar to the example that we saw, any 3 out of the 5, there is sufficient to recover the original. So in this MDS property, so you have any K out of N. Okay, so we will be looking to construct codes which have this property. Okay, so this is just the basic principles. Now let's see how codes are used in data centers. Okay, so when in distributed storage clusters. So in the data centers, data is stored in really large storage clusters, consisting of thousands to millions of disks, and they are all connected via a network, and storing petabytes to exabyte. Petabyte is 15, and then times 3 petabytes. Okay, so in such really large scale systems, failures are common. So it's like a day-to-day normal. And failures in these systems are measured using this annualized failure rate. Okay. So it's just means the expected percentage of the disk drive that fail in an year. Okay, so pictorially, you have lots of disks like this. And in order to protect data against data loss, data is stored redundantly. Okay, so one option, a small fraction of the data, could be stored using replication, as shown here on the top left, where you have 3 copies of this chunk. But the bulk of the data, most of the data, is stored using arrangements, like shown here on the right bottom. This is a 9-6 code. So you have 6 data and 3 copies. So this is how you kind of will be distributed in the system. So let's take this complete example of the 9-6 code. So how is it used in the system? So you take 6 data chunks. So many of these distributed file systems, such as Google file system, distributed file systems. So these are some distributed file systems that are used today in the industry. So they take 6 data chunks in this example. Okay, so different systems with different parameters. But in this example, in the 9-6 code, so you take 6 data chunks and you add 3 parity blocks. So just like the example that we saw where we have 2 parity blocks, here we have 3. So there's like 3 different functions. Okay? And then each of these 9 blocks are stored on a different disk, typically also on a different server, and also chosen the different what is called as a RAM. So these are all different failure domains, so that when one of the chunk fails, you don't have coordinated failures along the other chunks. Okay, so these are all stored in different domains. Okay, so coming back now again, zooming out, this is how the entire system looks like. Lots and lots of disks, lots and lots of data encoded and spread across different disks. Now, that question, the key question in this operation is how do we choose these parameters? Okay, so how did the system choose 6? Okay, so these parameters are chosen to meet the fault tolerance requirement. And these systems are often modeled using Markov chains, and the metric for mean time to data loss is used to determine the amount of fault. That's one metric. And there are also other metrics to keep in mind that all covers in deciding the parameters. And of course, the failure rate is this. The failure rate is higher, we have to use more dependency provided with that. But in today's systems, this choice is done assuming an average failure rate. So you have thousands of risks, you measure the failures, and then you take an average failure rate across all the clusters, and then see what is my mean time data loss metric and what is my availability requirement, and then choose a parameter. Okay, so we can say that this is one scheme for all risks. They are not differentiating the things. Okay. So we did a study on real world production disk drives from Google and Apple with millions of disk drives. And in this plot, you see the outcome of the study of the failure. Okay, so on the y-axis is the annualized failure rate metric. And on the x-axis are different make models. Make models refer to different companies. Like there are many different companies that make this types. So these are all different disks. So the main takeaway from here is that keep in mind the y-axis is in log C. So you have all sorts of magnitude variation in the failure rate. Okay, so all this don't fail together. So the different group of disks have very different failure rates, orders of magnitude. Okay, so now the failure rates not only changes across different groups of disks, it is also well known that it changes over time. Okay, so this is called as a hazard problem, which is also common in many other systems, including human beings. So On the y-axis, we have AFR, like a failure non-elasticity. X-axis is now the age of x. Right, so initially, there is a high failure rate, and it's called as infancy, or infant mortality. Right, so the failure rate is high, and then it comes down, and then it's pretty stable and low. It's called the useful life failure, and then the failure rate again increases. It's called wear out. Okay, so this is called as the bathtub because of its shape. Now this is a textbook curve, like a perfect bath. But in reality also, so the study from the disk failures also look like that, right? So this is from real data from Google and place testers. So you see there is infancy, useful life, and there are it's pretty vast shapes, right? So the failure rate varies across different groups, and it also varies over. Okay, so now this provides us with an opportunity to reduce the risk. Now, because the failure rate is low and pretty stable in the useful, we can use lower limits on disks which are operating in this regime, and hence it will help in reducing the storage. So in general, this idea is called this adaptive balance. That is, you will adapt the amount of events by changing the parameters of the framework to reduce storage. And from data from real world classrooms, again, Google and databases that I mentioned, if one does just adaptive, we can store around 16%, and even in some of those 25% in storage space, just by adapting the parameters of the code to different disks depending on their failures. And because of the large scale of operation, this translates to thousands of fewer disks hardware that is needed and millions of dollars, not to mention the savings of energy and operation costs. Okay, so was there a question?
I don't know.
Sure.
Really, why the percent of the reason?
Oh, the failure, the reasons are very different. So initially, the infancy period reasons are often some manufacturing defects, which testing, and as the firmware issues, but any kind of things that go undetected in the testing process. On the other end, wear out is just wear out, because over time, after using for a long time, like everything, like like laptops will wear after a few years. So similarly, that's just wear. Yeah.
That's not really that mean that the early on are removed from the market, or?
Good questions. So this that fail early on, so it depends on different companies and different scale of operation. So are you asking that entire batch will be removed or just this sector?
Let's say how does that like failing early on does not carry on onward?
It doesn't, yeah. So if it fails, it is removed from operation. Sometimes it is repaired and put back in, but that is considered like almost like a new this act. But often if it fails, it's just removed from. Yeah, if you want to. Yeah, good question. So feel free to stop me.
Sorry, can you define the failure rate? This includes the error correction in the software itself. So you have
Yes. So what is done in the hardware, this is all in the software.
So the only way this affects you is from the failure. But you assume that this can also protect.
That is, yes. So there is multiple levels. Okay, so now this is one reason to do adaptive code. That is change the parameters of the code depending on the field. But there are other reasons. Like for example, depending on the temperature of the data. The temperature of the data responds to how how much access is there for the data? If the data is popular, it's called data, and if the data is not popular, it's called old data. Okay? So if it is hot data, then you have to give higher redundancy because you have to be able to store more number of pieces and vice versa. So but this is another reason why you want to adapt the code parameters over time so and not make a standard choice. Okay, so this is all the motivation for doing adaptive choice in the parameters for the relation. This means, so this was all this is more on the it's all good. But this leads to a very interesting problem on the coding theory side, which is a more mathematical problem, and that is called a code conversion. So let's see what code conversion problem is. So when the failure rate of a group of bits change. So I mentioned that you want to adapt the code parameters to the failure, right? So we have to change the parameters of code, that is, we have to change n and k. Okay, so both n and k of the code will have to be changed. And one default way of doing this is re-encoding. That is, you put data already encoded in certain and one that they and I take. Now you have to change the parameter of the encode to some other parameters. So the default way is to re-encode. You read the data and you create the new parameters for the parameters that change. Right? So you read the data, create new parameters, and then write. However, this is highly resource intensive because you have to read all the data and then computing parameters and write. This is too high cost resources. So this is data from again real production cluster at Google. On the y-axis is the percentage of the IO of the cluster that will be consumed for such kind of conversion. That is, you are changing the parameters. And this y-axis is the date. So as you can see, for several days, 100% of the cluster IO will be consumed just for doing conversion. If you take the default. And this is clearly unacceptable because in a cluster, your main goal is to serve the IO requests from the workloads, not doing this kind of background. Kind of, encoding the data, changing the parameters of the data, all these are more background operations, so you cannot consume the requests. So this is a problem that needs to be addressed if one has to, if one can use this adaptive. And this is what the code conversion problem refers to. So basically, you want to convert data that is encoded under an NIKI initial code into data encoded under NFK of final. So you have NIKI, so we call the parameters N and K. Now we want to change the parameters, right? So you have data encoded under CI, which has NIKI parameters. Two data encoded under CI, which has NFK of parameters. So let's call this initial configuration, and this is the final. One thing to keep in mind is the same data, the same underlying data, same information is stored, but how it is stored is different. Okay, so at this point, I want to highlight my PhD student, Francisco. So the next the most the theory work that I'm going to present is work with Francisco, and as many of you might know, he was an undergraduate student here at UC. And I came to know about this space via Francisco was a great student to have. And one of the goals that I had here is to encourage community to apply, to see if you think about okay. Yeah. So now going back to code conversion problem. Now, in order to study this code conversion problem, so we propose a new framework for conversion approach. Now, the main challenge and main difference from the existing approaches is the fact that when we want to do the code conversion, we want to be able to handle a change in this dimension, which is this parameter k. Changing, if we keep k fixed and just changing n, there are existing approaches that don't handle that much. But when we want to also handle the change in dimension, that is when we need a new approach, and that's where work on the multiple cores.
Sorry, how you do the setup or
No, so we never have copies. It's the same data block, so I will pictorially show it. So we basically start with LCM of Ki and Ki matrix of the data blocks. And this is what is different from many of the coding theory problems, where the key essence of the problem can be captured in a single code in almost all existing problems. But in order to model code conversion, we have to have multiple code words in which. So let me show you pictorially. So we are going from NIKM to NFKM. So pictorially, you have some number of initial code words. So recall these empty boxes are original data blocks, and these filled boxes are variable blocks. And you have M is the LCM of Ki and Ki. So you have M over Ki code groups. So these are all different code groups, different data for the same code, right? Same mathematical function is used to generate disparities, but on different data. So you have M over Ki initial. Now that has to be changed because we want to change the parameter of the code. Now it will go into certain number of final code groups. So you have these are KF, now the data blocks, and these are variables. So these empty boxes, the data blocks are the same as the data is the same, but the parities are right. So you want to go from initial configuration to parity. So let me make it even more concrete by taking this example. So let's say we are going from 3 to 4 to 5. And LCM of Ki and Ki is 6. Right? LCM of Ki. So we start with 6 data blocks. Let's say it's from now, initial code is a 3-2 code. So you encode 2 blocks together, right? So let's say AB is encoded together, CD is encoded together, BF is encoded. That's how the initial configuration looks like this. Now, after conversion, we want to change the parameters to a 5-3 code. So let's say, because now we have to encode 3 of them. So let's say we encode ABC together and DEF. So it looks like this. That you went from a 3-2 code to a 5-3. So now this is ABC, this is DEF, and these are. So is the setup clear what code conversion problem is? Okay, so now there are different types of conversions. So we have identified multiple different kind of building blocks of conversions, which can be used to address any general conversion on any enacted. So the main fundamental types of conversions are called as merge and splits. The merge, as the name suggests, is merging multiple codes into one single. And split is the opposite, where you take one program and split into multiple. Okay, so these are like 2 different types of conversions, which can be used as building blocks to do general conversion for any enacted value. And there are different causes of conversion that matters in the real system, which we will extract and model in the The first cost is the access cost. That is the number of nodes you have to touch. Either you read or write. That is called as the access. That affects the system because it kind of goes and cubes into the system and then takes up the. That's called the access cost. And there is bandwidth cost, so called as conversion bandwidth, which just refers to the total amount of data that is transferred across. The amount of data that you read. This is just the number. This is like the minimum cost. This one is actually count the total amount of data that is spent. Okay, so both access cost and conversion bandwidth matters to the real system. So we have modeled both of them. So both of them kind of uses different mathematical tools in modeling and solving. So we have works looking at this merge and split regimes in the access cost and then combining them to address the general regime that we found in that we have. And similarly on the conversion analysis.
Like minimum bridge.
Multiple beliefs. You mean you can you can read. I will give an example. Yes, you can read from any, but you will have a cost. So if you read from more,
Yeah, that's actually the problem that's a single pass.
oh, yeah. So the one I don't know that you have a single, just one, but you can do multiple if it helps. But I haven't.
Okay,
Let's. So there are so we've looked at both access cost and conversion bandwidth and split and merge and general regime. On the conversion bandwidth side, there are still many open questions. So we don't know the general regime solutions. And in the interest of time, I will focus only on the access cost and also I'll give a flavor of the results only in the merge. So in the merge regime and for the access cost, here is what the table means. Recall R is n minus k, it is the number of parameters. On the y-axis is RF into the final. And on the y-axis is the relative savings, which is basically the percentage of saves. 0.6 means we save 60% of the access cost as compared to the default. We call default projects. Reading the data, creating new parameters, newly, then re-encode it and then write. So this is savings compared to the default. So I'm stating the theorem in an informal way, like just putting in the figure, avoiding using the mathematical formula here to avoid the clutter. So basically, in this regime, that is when we have RF less than 100, you have access cost, which is lambda I. Lambda I is the number of initial purpose that you have. So you can save significantly as compared to the default. But when Ri is greater than Rf, you cannot save anything when compared to the default. This is all under the requirement that both initial and the final code have to be NDS. So we call it mentioned NDS property. It's that any K should be sufficient to recover the data out of n. So both initial and final code have the same. And under that constraint, this is the result. So you cannot save here, but you can save. And so, of course, the next natural interesting question is then how do we construct such codes which help in reducing the resources consumed as the primary. And recall, designing a code is designing this parity matrix, right? So we construct this codes by identifying what the properties that the parity matrix is in order to meet that bound. So that table is an upper bound. That's the best model. Now we have to construct a code that can meet that. Right? So the first property is that as I mentioned, we want the code to be NDS. Right? So for that, we need this super regularity. And then we introduce a new property called block constructibility, which will help in making the code conversion, make it efficient code conversion for. So first one is super regularity. So that's first for the NDS property. So super regularity, as you might have seen, right? So is that every square matrix is invertible. So this, recall this, we want to construct a matrix where elements come from a point. And you want it such that any square submatrix is full of invertible. Like for example, if we remove all these columns, what is remaining should be invertible. Okay? And that should hold for every such square. Okay, that's what I should do. And if the parity matrix has super regularity, then the code will be a base. Okay, so this is the first requirement, because we want both initial matrix, the final matrix to be MBS, right? So we want both initial and the final year to have this one. But this is about only MBS, it's not doing anything for conversion. For conversion, we want this new property called as block constituent. So what does that mean? So remember we are being merged, right? We are merging the folders. So what we want to be able to do is, we want to be able to construct the final parity matrix P by taking this initial parity matrix P and then doing some mathematical operations and putting it together, stack it up and be able to construct here. So you want to be able to construct PF using PI, and that's what we mean by block constructed. And if we can do that, then you can do the merge and create the final parity using the existing parities. So I will give a concrete example of what in a minute. Okay, so here to here, again stated informally. So we can construct access optimally convertible ports in a merge regime when the field size is large enough. If when the size of the field is large enough, this construction is possible. And by access optimal, I mean that we can meet that bound, the upper bound that we show in the video. So now how does the construction look? The construction looks like this. So you take the primitive element from the family, and the form of the matrix is of this form. Okay, so the both PI and PF have this structure. So you have theta with the square, the words. So similar structure is there here. Okay, so it's if you are seeing the Van Der matrices, so it's a kind of matrix, it's a fixed structure, so it is similar to that. And how does the first question, how do you construct conversion? Now, this is a conversion for going from KI3 RI3 to KF6 RI3. Okay, so this is a merge. So we are merging, right? So we want to be able to merge to create this. So the conversion process reads only the context. So during conversion, you are not reading the data. You're reading only the existing parities created in that. And this is where the savings come as compared to the default. The default you have to read data. So here you read the existing parities from one code. So here you see KI is 3, KF is 6. So you have two codes being combined into one. So you take these two parities and then add them. You take these two parities and do this linear combination, and similarly you take these two parities and do this linear combination. The linear combination vectors are these are elements for this. So it's what you can see is you basically have this block constructible property, right? So PI, you can see that PF can be constructed using PI. So first copy of PI is here, and certain specific linear combinations, that is multiplying this by theta to the 3 and this by theta to the 6 gives this. This is the block constructible problem. So, and then super regularity needs to be checked, but that is where the high field can be found. So you can just write this as a polynomial and you want it to be 0, then as a field value is if the field size is bigger than certain amount, then you can find this element such that, and that will make it super.
I think this is constructed finding the B. There is an algorithm to finding the space.
Oh, so this construction is existent.
Oh,
Yeah, so that is you can.
yeah.
Right.
Oh,
We have an explicit construction. Okay, so this is it. So now everything that is very high and that's the existing children. We show that if the field is large, you can find an element such that the property. Now, of course, in real system, you need low field size. And we have some work in that direction. So again, stated informally, for certain parameter regimes, specifically when R is strictly less than R, okay, not when less than or equal to, we can construct, this is the next one, we have constructions which is low field size and without cluster. So I'll just show at a very high level how the construction. So this construction uses what is called as super regular mechanical inverse. So it's a matrix with this certain form. So it has this, so you can see from the bottom left to top right, they are all identical elements, right? And this is called a mechanical inverse. And this helps us with that block constructible property. Okay, so we will choose the PI and as shown in the pink here. So these three, so this is Ki equal to 4, I equal to 3, K equal to 8, I equal to 2. So again, 2 4% merging into 1. So we will choose Pi as the pink ones here, and Pf as these purple ones. So as you can see, using these two pink columns, half of the Pf matrix is covered. And because of this angle structure, the same column appears here in the second half of the here. So because of this, we again have this block constructible property, and you can do this kind of conversion. So when converting, you will read the first two parities from the first forward and the last two parities from the second forward. And you can do a linear combination. In this case, it's just direct addition. So there's nothing more to do. So just direct addition will give you the two new parities. Okay, and that structure gives the structure that I just explained makes it block constructible, and there are existing algorithms to construct such angular which helps in
How does that work? No.
Oh, so that construction, constructing the angle rates. This is an existing work from way before the design of the course, because as I mentioned earlier, the super regularity property needed for constructing this course. And it is pretty simple, it is not complicated. And for example, in this example, it will give you with 30 input size, pretty low field size, and covers pretty good when you look at this.
And the other one, where you require the one to show people the data.
Yes.
That only works for large people.
Very large pieces. It's like almost, yeah, it's like double S.
Oh, wow.
Yes. Yeah. Yeah. But that's it's just existence. Yeah. And yeah, so this is the more low field and more practical. Okay. Now any questions on this? But I know this is very almost I was finishing. Again, I mean, happy to take more questions. So, given the time, I think I will end here. And before going to the summary, again, want to acknowledge everybody who's there. I'm just going to know right? So, the students, collaborators, and CMU, and also the operators, and funding. And so, going to the summary, I want to emphasize that coding theory is a super useful tool, which is relevant in today, both on the theory side as well as the practical side. And I showed how arrangements are used in real world large scale distributed storage systems. We saw a new coding theory problem called the code conversion problem, which is arising from adaptive coding systems. The course is a general framework to study the code conversion problem. There are many open problems in this space. So today I will get back to go into the details of it. If you're interested, we have an IEEE Bits magazine. It's a new magazine from the information community, where the articles are written at a very high level, so that it's like new problems are introduced. So we have a article coming up, the next issue, which is a special issue on storage. So the article title is Core Convergence Storage, so that can give a very helpful overview. And if you're interested in anything, you can an email about the conversation with the reports. Thank you, and I'm happy to take questions. Yeah.
So if you read code again, like what happens with the data? Because then you don't have rows next to each other. Like we have,
Oh, so those are not really so much. So one of the big things they are all in fact, they are the same as part of the problem. So those they have not three remain where they are. Just the old paradigm to be created and after the work, the new paradigm.
Is there a locking system so that if the failure during the report?
Yeah. So here, the original data is not built. So you're reading, re-encoding, and then only after the new data is looking. So it's kind of a lot.
Yeah.
I could make it quick.
Yeah.
Very much business. And also people, you are, you have this, being object to kind of setup, you know, that you define the code.
Yeah.
But, and then we get some redundancy, which is very big, but, there's some other way. It is more than this.
Yeah, very good question. So all that I introduced today are termed as linear codes. So because of the linearity property, so this code concept of linearity property, because of which we are able to represent the values, right? But in general, codes can be on. And this is where, as you mentioned, basically what the code is, you have a space F to the N, right? In that space, you are choosing some Q to the K because there are K and singles Q to the K points. So in basically picking points of this. Linear codes restricted on your picking because you have to be able to become that as it's part of the generic units. But you don't have to do that. You can pick any one you want, in which case the code would be non-linear. But non-linear codes have downsides to the given because we cannot represent it as units. Encoding has to be done via lookup tables, like which message points to which code cannot be succinctly represented. Linear codes, it's a native approach. You get the message, you multiply the native to the code. So that's not there for non-linear codes. For the reason, almost all codes used in practice are linear codes. But if there is significant benefit, one can consider, but so far, other than in some specialized scenarios, I had an example, there hasn't been much advantage of linear code, non-linear codes. Yeah.
Well, I mean, using one presentation, like you store data. Every time I want to change one of the data, I think it will update also the redundancy policies somewhere else.
Yes.
That sometimes it is like that.
Very, very good question. We're talking about what is called an update operation. When a data has to be updated, the parameters also have to be updated. That's definitely one of the metrics of interest. And there are codes that you get optimizing the update cost. That is, can we define the metrics such as update cost can be reduced? In fact, along with Francisco, we have one looking at the update cost. In specific head. For endless codes, you cannot reduce update cost because MDS problem requires that every parity becomes every database. Because you want any K to be actually recovered in the any class of nodes. Yeah, updating complexity is the worst for MDS codes. But there are scenarios where you don't need MDS codes. In which case you can optimize for the same cost, which is what we look at in other work where we call it an MDS code, minimum billion cost. But there's definitely a metric.
So, it's very rich, there like this, quantum figure, right? Is there any possible gain by picking, let's say, the partition of the price in a smart way? Like maybe it's a good idea, like it's a good idea to keep the fund in the same set of things. Very high rates, but those gain out of so
Oh, very good question. So this is more on the system side, right? How you create the data and how you define the data. So in order to do it in the coding, we have had multiple system designs. Initially, we wanted all the blocks of the data to be stored on this the same variables. But then that requirement is restricted in real world systems in order to identify the same variables. And we have since then evolved the system design. Finally, now allows us to store the data on any variable. So you might have chunks from code work stored on this different variables, but that's taken into account in the calculations of the calculation. So you can store with different variables. Some of them will be high risk, some of them will be low risk. But the choice is not made explicitly in order to optimize. It's just that you choose the risk where you will go along, then you will get some variables. Some of them will be high, some of them will be low. Then you choose the parameters based on. But yes, for your specific question, well, think about doing that and see what we're going for. It's definitely possible at this level. So you're asking within the partition, within the disk, that is a little bit more involved and often handled by this firmware, not at the file system. File system level is more handled at this at one entity, storing on the disk rather than which one. But I will have in the firmware level and the disk handles. Very good questions. Any other questions?
Okay, so the classic fail of for the hard disk died, but if you have a rupture in the data, how do you know?
Yeah, very good question. So basically, there are CRC checks that are both within the disk as well as across the disk and the file system level. So periodically there are background operations which keep doing the checks and keep and compare and see if the checks pass. And this will identify if there are defects. In terms of failures, as we mentioned, you will know you will not get the response. Yeah.
How often are these non-conversion making the daily basis or way?
Yeah, but so currently, conversions are done for some other reasons, which will over. It's not daily, but in the adaptive coding approach that we are proposing on the system practice, this would be a day we will measure the every day, and then you will see that the value is going to be changed. And I will move to the initial plot or the peak second. Yeah, that is the plot over and over. And then we see and make a decision every day, but it's not that every day conversion will be made, but it's decision will be made with daily basis. And some of the days conversion will be made. So this is on the system side, the adaptive coding idea has been part of a lot of prevention for industry. So we're currently working with Google, adding this character elements into their. Yeah, in access to the.
Okay, let's be fine.
Thank you, thank you.